All right, y'all know I'm on that grind. Got another video. Um, Anyways, on a serious note, we're gonna talk about this really cool question called random numbers. No, not random numbers, but random numbers. I really like this problem, because it's sort of those problems where you can make it really hard for yourself if you pick a solution path that is like too mature for you, or if you just think really simply and really basic and make basic observations. This question is really, 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 really easy. Um, but but this question is also very, very difficult in the sense that you could pick a solution path that leads you to sort of um, making it more difficult than it is, and that's what I did at first. I tried to do some DP on here. My states weren't good, and it was sort of just annoying. And then I did the greedy solution, and it was cleaner. And that's why I theorized this question as an 1800. And just for an 1800 for a Div 2C is very difficult. That means like 1,200 people solved it or something like that. I don't know the exact number, but usually that's what it means. And so for a Div 2C, this is usually very difficult if it's 1800. And I don't think it's actually a very difficult question if you do it the right way. And it really makes some basic observations. You don't have to like have some crazy intuition, but it really just makes some basic observations. And Again, this is saying sort of like try to think greedily. I guess not. I'm not trying to say like don't always do greedy before DP, but greedy solutions tend to be just simpler in general. But they don't obviously always work. DP is more consistent in that regard. But I guess we have this question, and so you basically have a random number, which is some contiguous string of A, B, C, D, E, and their values are depicted here. A is 10 to the 0, B is 10 to the 1, C is 10 to the 2, D is 10 to the 3, and E is 10 to the 4. So in general, if it is the xth letter in the alphabet, it's 10 to the x minus 1, if you want that. In this case, this only extends for 5 letters, and so that's pretty interesting here. Anytime you only have 5 letters, why would it not be like 26 or like something more? You should sort of keep that in mind. That's sort of special. Maybe we can take advantage of that. Definitely, that's what the greedy solution does. That's literally what it does. But the idea here is we basically to calculate this number. Um, each of string or character represents a value, and the value is positive or negative depending on a couple of things. So, for instance, this D over here is negative because um, for all the letters that it sees to its right, it can find one letter, at least one letter that is strictly greater to it than it, which is E. And so, if that's true, then you negate it. If it's not, then you don't negate it and you just keep it positive. Our idea is that you can change no more than one digit, so you can keep the string the same, or you can, I guess, replace one character to make it better. And so the first thing you should be thinking about is how do you calculate the random number? It's very, very, very easy. If that was the question, in fact, if it was just like you can't change anything, what's the value of this random number? That would be like an 800. It would be an 800. All you do is pretty much you can loop backwards. You can either pre-compute suffix maximums, but looping backwards is just cleaner. Loop backwards, keep track of like the max character you've seen, and if that character is greater than or equal to the max value, then you know that it's going to be positive, and if it's not, then you know it's going to be negative. And yeah, this is like an 800 problem if it was no replacements, and that's just like it. It's a pretty basic function. So that's the first thing you should be thinking about. So that's pretty easy. The second thing you should be thinking about is what happens when you replace a character. I feel like if you ask this sort of question, it sort of primes your brain into thinking about the greedy solution. Because let's take a string, for example, like this one here, and this was like the fourth test case. Let's say I just go to some letter A and say, let's say I replace it with B. Like I'll just pick some arbitrary letter to make this solution not seem contrived. So I'll just replace this one with B, and then we have like B, B, D, D, and whatever. So the idea is that if you replace some letter to B, think about it. Then what letters get affected is the question, right? That's what we're thinking about. Because a replacement affects a string. So what positions get affected? Can the positions to the right of B get affected? No, they can't get affected because the position the sign of a number only depends on the characters to its right. And therefore, if B gets changed, its characters on the right is to B is the left of. So these characters, for what I'm saying is that if you I'm saying that these characters in this index, like these characters cannot be affected because they're all to the right of B, and their sign is only dependent on the characters to the right of it, and obviously B is to the left. So you know that, okay, well, that, this part won't have any effect. Um, then you note that what characters can get affected. Well, obviously characters to the left, because you're changing what those characters to the left can see to their right, right? Now D can see B to its right, right? Or, I mean, technically it could before, but you know what I'm saying. You're possibly changing what these characters to the left of the character replacing can see to their right, and so basically the only characters that really get affected um, is the prefix before the letter you're replacing. These are the only letters that could possibly get affected. Everything, the suffix does not get affected, but this prefix could. And in fact, and then now you ask yourself, well, does it get negatively or positively affected? See how we're like asking questions, right? Well, if you increased, if for some position, we know that we went from A to B, and so now the characters to the right, to the left of the character replacing, which is B, now see a higher letter than before. And we know what happens when you see a higher letter. If it's high enough, then it will negate that position. Therefore, if we go from A to B, we know that uh, we know that it might possibly affect some numbers negatively. So the idea is that, well, intuitively we would want, if we are going to do some replacement, we would want it to have the least possible effect. Um, and so what we would do is that, why would I replace an A with a B? Like, if the optimal solution was going to replace an A with a B, why would I replace this A with this B? I would just want to replace um, this A with B, because I know that this replacement is going to possibly negatively affect a smaller prefix. So can we generalize this? What can we take from this? So we can make this in generalization. If the optimal replacement, consider, now the first case is that we don't replace anything. In that case, we can just easily get the value in the function, right? But the second case is that if we choose to replace something and that optimal replacement chooses to increase a letter, then I claim that what you should do is you should always choose the first occurrence of the letter you're replacing, because the first occurrence will affect a smaller prefix, right? It's going to affect a smaller prefix of these letters. And because it affects a smaller prefix of these letters, you should always replace it should always be the first occurrence. So in fact, you don't even have to, I'm pretty sure you could just replace the first non-E. That would obviously be always beat everything else, I think. Or no, that's not necessarily true. That's not necessarily true. But it doesn't even matter because you can try all of them. There's only 5. But the idea is that if the optimal replacement chooses to increase a letter, it's going to be the first occurrence of the letter you're replacing. So the idea is that there's only a couple options. There's 5 options. You check A, B, C, D, and or I guess E, but you'll see why that doesn't really matter. And you only care about the first occurrence of these if in the case that the optimal replacement chooses to increase the letter. So that's the first case, right? Or the first case is that it doesn't choose to increase the letter. That's pretty trivial. It's just plugging into the function. The second case is that it does choose to increase a letter. In that case, since we want to negatively affect a prefix as small as we can, it should only be the first occurrence, because the first occurrence will be most left, and then this prefix is as small as it can. And then the idea here, the idea here is that what letter should we increase it to? Greedily increase it to E, because sure, I increase some letter to B, but greedily increase it to E, because E is always positive no matter what. It doesn't matter what it sees to its right or what it sees to its left. It's going to be positive because there's nothing to the right that will be strictly greater than it. It's the greatest one. So obviously greedily increase it to E. So that's what we do for the first case. We note that we can keep track of a scene and we only care about the first occurrence of these letters. And what we can do is we can replace that index with E, and then we can just get the value and just get the best one. But that's the first case, so that's for answer 2. What about if the optimal replacement chooses to decrease a letter? Because again, A replacement is either going to, again, this is asking ourselves, what does a replacement really do? It either increases or decreases a position. What happens if it decreases a position? Well, if it decreases a position, this is slightly trickier. The reason why this is slightly trickier is we just have to try a couple more options. I guess I'll go back to this case, right? I'll pick like maybe some, I guess I'll choose, I kind of want to do this E. I'll put an E here. Let's say I choose to replace that E with a C. So think about it. When we decrease a letter, right? What letters get affected? It's the same thing. The prefix will get affected. The suffix is not going to get affected, but the prefix could possibly get affected. Um, and that position also might get affected too. Because if you decrease a letter, you decreased it from C. Now C now obviously C can see now C this suffix can negatively harm C more than it would have if E was in that position. Because E can't, anything that C would write won't affect it, but C could possibly be affected by that suffix. But just think about the prefix first, right? Just let's think about the prefix first, not think about two things at once. For the prefix, if we choose to decrease a letter, we choose to decrease the letter from E to C, uh, then we note that that prefix can be actually positively affected. This intuitively makes sense because an increase it was negative and now it's nice, so it's sort of symmetric. But unsurprisingly, we note that if you choose to decrease it, the prefix can be positively affected, right? You can positively sort of affect this prefix, and then so the idea is that you can positively affect a prefix. So then intuitively you might say, oh, can we greedily positively affect prefixes? How do we do that? Well, it's sort of symmetry here. You choose a last occurrence, um, the last occurrence of that, and we don't know what. And then now, so we might think of the last occurrences, which would be C. Like this has a bigger prefix, and it's positively affecting a bigger prefix, and therefore, that's greedily better. That's more optimal in that state. But then you're asking this yourself, what about the suffix though? Because the suffix also the suffix can only affect the position you're replacing because it's again, and the idea is that if you're going as rightmost as you can, the suffix is smaller, and so therefore that suffix, if you the smaller it gets, the lesser chance it can negatively affect the position you're replacing, right? So for example, if this is the position we're replacing, then this suffix can affect this, right? But for replacing this position, right, this one, then this suffix can affect this, right? It's a smaller suffix, and so the idea is that the smaller suffix can negatively affect it. Smaller suffix, then the least amount of harm, the lesser harm that it does on that position you're replacing. So intuitively, if you try to greedily optimize the prefix, we also in return optimize the suffix because we're also making the suffix really small, and therefore the suffix won't affect it as much as we can. And so the idea is that we only care about the last occurrences of the letter, of these letters. If we were going to replace a letter, then it would obviously just be some last occurrence. If it's not, and you can prove this by contradiction. If it's not, then you can always improve the answer by making it the last occurrence. And then so what do we choose to decrease a letter to? This might be a little bit more unintuitive because I guess we chose to decrease this letter to E, but why not choose to decrease it to A, right? Or to C, I mean. If you decrease it to A, then the letters that it sees to its right um, will have a higher chance of affecting A because it's smaller. But also A could have a higher chance of affecting the prefix because now it's A is smaller. So what do we do? Well, you'll notice that there's only 5 letters. So for some position, we can just try decreasing it like down, for example, for D, try decreasing it down to C, to B, to A, and then for C, to B to A. And in general, for some letter J, try to decreasing it down to J minus 1, J minus 2, all the way until you get to 0. And this is in terms of like their values. We're mapping A to 0 and B to 1, and in general. And yeah, that's basically all you have to really do. It's really the same thing as the decrease. Instead, you just have to try more options. And even if you didn't know what to do for the increase, you could also try all the options for the increase. It just so happens that we can directly just go to E because we know it's going to be the best. But for the decrease, it's not exactly the same, but we just try all options. And there's not, this is going to be at worst 5. And therefore we have just, constant amount of really options we're trying. And we're constantly calling this linear function. So the overall time velocity would be linear. And so the implementation of this is, this is our get value function, which just gets a value of the random number. And then I have this worst. This is just the worst case. I mean, this is just, you could just put negative infinity. It doesn't really matter. But the main idea is that the first case is that we don't actually replace a number, right? The second case is that we choose to increase the first occurrences of each letter to E and get the max. And then the third case is we sort of go backwards and get the last occurrences, and we choose to replace. We choose to decrease them down to all the possible letters that they can be decreased down to, and we get the max answer. Then after all, we just try the best. And yeah, that's it. That's literally it for this problem. It really isn't that deep. This is an 1800, but again, sort of just if you can sort of think simply, make some basic observations, you should be able to get this question. It's really not that bad. This is all sort of just like, don't overthink problems, I think. And I think a lot of people overthought this problem, including myself at first. Don't overthink problems. And don't try to do too much. Like, don't try to make a fancy DP. Just sort of simply think or simply look at a question and you'll be fine. Yeah, that's it.